Okay, so I'm going to give you a course of lectures devoted to point processes, and we will consider some models and some properties that arise here. And today, on the first lecture, we will see some motivation for definition of a point process, and we will start from some first examples, and we'll see that some common distribution arises here, and we will see some connections between them. Informally speaking, the point process can be considered as a model, mathematical model that describes ensembles of points or particles in space. Usually here can arise some misunderstanding what is a process, because usually we understand a process as some random variables that depends on time. So when you speak about a process in general, you assume that you have x of t, where t is time. But now this is not the case in this theory. So this is not that you should think about here. So here a point process is a model that can describe particles in arbitrary space. So here you can imagine two-dimensional space or three-dimensional space, and we will have ensembles of particles that can somehow depend one from another. So you can imagine a particle of gas or bosons and so on. So you have some structure in space. But this terminology comes from historical point of view, because the first example of a point process was a Poisson point process, which describes in time the occurrence of some random events. So I think most of you know that we have some example of a Poisson process. So it describes that in time some event occurs, and we just count the number of these random events up to time t. So we have such a picture. So historically we have these names, but how you can imagine this picture? So you can just draw on a real line, if this will be real line. So you can just write here these random points, yes, and these random points will correspond to this point process. So here you can see one-to-one correspondence between ensembles of particles on a real line, and a Poisson process that you are familiar with. Okay, so this is some brief introduction to terminology, why we call this process, but later we will consider processes not only on the real line, but in general case. Okay, and now let us start from some simple examples. So we will talk more about Poisson process here, but start with very simple example. So if I talk about a random ensemble of a particle of some two particles, I can start from a model with one particle. So let us consider interval, for example, 0, 1, and let us assume that we detect in this interval a particle with some probability p. So I will write detect a particle, one particle, with probability p. So here we can find or not find some particle. So let us denote by x the number of particles on the interval 0, 1. So this is very simple random variables in this example first. So now this random variable can take only two values, 0 if we do not see here a particle, and 1 if we detect here a particle. So with probability 1 we detect a particle, and with probability 1 minus p not. So this is a very simple example, gives us the Bernoulli distribution. So X is Bernoulli distribution with parameter p. So this is very simple. Now let us consider example second. So now let us consider, so assume that we have machines that can now detect not only one particle, but it divides the interval 0, 1 into n equal intervals of length 1 over n. And again, assume that we detect or not detect a particle on each subinterval with equal probability p. So I can find here or not find a particle. Okay, so what do I have now? Let me denote xi. This is the number of particles on subinterval I over n, I plus 1 over n. Okay, so now xi is has a Bernoulli distribution as from the previous example, but now we will consider the total number of the particles in the interval 0, 1. So this is total number of particles on 0, 1. So from this we can write x as sum of particles on the intervals 0 to n minus 1. And here you can recognize the binomial distribution of this x. So I will just write that x is equal to k with probability, so and k binomial coefficient, and as I said, we detect a particle with probability p and not detect with probability 1 minus p. Okay, so we have binomial distribution here. So I will denote it later binomial with two parameters, n, because we have a total at most n particles, parameter p, and this is k. Okay, so I think that this is obvious for you, but if you have some question, please ask me. From 0 up to n minus 1. So here we obtain binomial distribution. Here, when we consider such a model, when we just divide intervals into equal subintervals, and probability to detect a point is equal to and fixed. But what if the probability to detect a particle natural can depend on the size of the interval, and if we will divide the interval 0, 1 on smaller and smaller intervals, subintervals of size 1 over n. But the probability to detect a particle, assume that it depends on size of this subinterval. So with notation of the previous example, now let us assume that probability to detect a particle on subinterval I over n, I plus 1 over n, is equal p small with index n. So what we will do now, we will divide interval 0, 1 on smaller and smaller subintervals, and of course the probability to detect here a particle will be smaller and smaller. So this is like natural assumption. But so the question is, if I consider again the total number of particles again, and what will be the limit distribution of this total number of particles if we will tend n to infinity. So here we will assume that Pn will increase, will decrease, but not so fast. So assume that if we multiply by n, then we will have in the limit some fixed value gamma as n to infinity. So under such assumption, let us see what is the distribution of total number of particles here. So as from the previous example, we know that this is the binomial distribution. So I write binomial coefficient But now here our P depends on N. Okay, 1 minus Pn and minus K. Okay, so let us write it more precisely. And here I have N factorial, K factorial, and minus K factorial. And since I know this limiting property, I will order it like this to use this property. And I should divide by N to the power K. And here also N Pn over N to the power N minus K. Okay, so now let's tend to N, we will tend to infinity. Let me write it in one more, what depends on Kn minus K factorial here. So this part I know tends to gamma over K factorial, and this we will see. Let me write like this, and 1 minus Pn to the power minus K. Okay, now in this representation, it's more easy to tends to the limit. So this, okay, let's term by term. This tends to gamma to the power K over K factorial. This one tends to exponent, so I know that this is tends to gamma, so this is exponent to the minus gamma. Okay, this tends to 1, and this one also tends to 1. Why? Because here we have exactly K multipliers, each of them tends to 1. So as summation, here we can recognize a Poisson distribution. So in the limit we have minus gamma to the K over K factorial. So this is a Poisson distribution, and we will denote it Poisson with parameter gamma. Okay. So here we see that now to give the picture, what can we see here? That if we have here whole interval, then probability to detect somewhere, no one knows where, but somewhere detect exactly K particles has a Poisson distribution with parameter gamma. So this is very simple examples that gives us motivation to consider in more details Poisson distribution and its connection to binomial distribution. So now we will talk a little bit about a Poisson distribution. I believe that almost all of you know some basic properties, so but you can just recall your knowledge and solve this exercise. So how to calculate the first moment of, if x is a Poisson random variable with parameter gamma, then the expectation is equal to gamma, and it is useful to know probability generating function. So probability generation function is equal to e to the power gamma s minus 1. So just as exercise, it's useful to know how to derive it. Now I want to discuss some interesting properties of characterization of a Poisson distribution, and we will see later that this characteristic property can be generalized from just random variable to Poisson point processes that we will consider later. So here I would like to give this some proposition. So some characteristic, some characterization of point distribution, Poisson distribution. So assume we have random variable, let x be, I will write notation here, random variable with values 1, 0, 1, 2, and so on, be and 0 valued random variable. So then X has Poisson distribution with parameter gamma, so it's Poisson gamma, if and only if for every function f from this set natural number plus 0 to r plus, we have the following properties. That's the expectation x f from x is equal to gamma expectation f of x plus 1. So this property is somehow characterize the Poisson distribution. So, and it's interesting because here we just use some moments. Yes, we should verify it for every f, but here we use this such moment that some sort expression from x plus 1 you can write in terms of f from x. Okay, so let's try to prove this. So in there, if I know, so let x has a Poisson distribution with parameter gamma. So we just need to prove this equality, and this is not hard. We just should write the expectation by the definition. So k from 0 to infinity, and here we know k, f from k, e minus gamma, gamma to power k over k factorial. So here the first summand is 0. So this is a hint for us that we can somehow change the index of summation. But so I will write here. So I can write from k from 1 to infinity. And this k and this k factorial will give me k minus 1 factorial. F from k, e minus gamma. And let me write here k minus 1 also and put 1 gamma here. I'm sorry. So now I can do change of summation. I come back to k from 0. Now I can write, if I write k from 0 to infinity, then I will write here just k factorial, but here f from k plus 1, e minus gamma, gamma k. So I just did a change of index of summation. Okay, so this is what we have. This is just expectation, and here f from x plus 1. So this is easy. Now let's prove in another direction, and here assume that we have this equality. Let me put here star, assume star is true. Then, okay, let me write it. X f x is equal to gamma x plus 1. Let me take specific f here. Let me consider f is equal indicator of 1 point k. Since I know that x is an zero valued random variable, so it is reasonable to substitute it. So I will have here expectation x, indicator that x is equal to k. I have this equality, and here indicator x plus 1 is equal to k. So the left-hand side, if I know that x is equal to k, then here on this subset of events, x is k. So I just write k times expectation of indicator is probability. K is equal to gamma, probability x is equal to k minus 1. And here you can see recurrent expression. Let me write here. X is equal to k. I can write it k, probability x is equal to k minus 1. So if we will continue this equality, we will get gamma to the power k over k factorial, probability x is equal to 0. Okay, so, and if you know that this is probability distribution, you should have that all these probabilities over k amount to 1. So this should be just e to the power minus gamma k factorial. So this proves that we have exactly Poisson distribution of X. So this is such a characterization of a Poisson distribution. Now let us consider some connection with Poisson and binomial distribution. Of course, we saw that the a Poisson distribution can be obtained as a limit of binomial distributions when we have increasing of number of particles with smaller and smaller probabilities. But now we will see that, that there is another connection. So I will write here relation between Poisson and binomial distribution. So let us start from some proposition. So let us consider two independent Poisson random variables, that X and Y are independent, and both have Poisson distribution, but with different parameters delta. Okay, and then okay, we will have here maybe two conclusions that X plus Y will be again a Poisson random variable with parameter gamma plus delta, but how we can connect it to binomial distribution? So if I consider the conditional distribution of one of them, so when X is equal to K, if I know that in sum you have some fixed value, for example, n. So it turns out that this conditional distribution is binomial distribution. So I will write binomial distribution with which parameters? N at total, probability to detect a particle gamma plus delta here, and K to detect here K. So how we can interpret this result? So if we have on some interval, we have two types of particles, X, for example, and Y. So we do not know what is the total number of X's and total number of Y's we have here. So this will be X's, the point that corresponds to X, and this to Y. Then this proposition says that we will have again at total. So we consider the summation. So if I consider all points together, then we will have again a Poisson distribution. But what is The second property about that if I know the total number of points here, so if I know that black and red points together have n particles, then the distribution of number of axes now have not Poisson distribution, but of course it under this condition it cannot be bigger than n. But it turns out that it has binomial distribution, and this is interesting as for me. So this is like a connection between two independent Poisson processes and their sum. Okay, let's try to prove it. And when you see here, so we will prove these two statements together by considering the following probability. So if I will calculate this probability is equal to n, and if I prove that this is a product of a Poisson plus multiplied by binomial, then this is all what I need to prove. Yes. So the question is, this is Poisson. So X has just a moment. Summation. So for summation, I will have a Poisson distribution of such form, and then binomial with these parameters, gamma plus tilde k. Yes, and just taking the definition of conditional expectation, I will have the second statement, and if I will sum over k, here I will have 1 after summation over k, and so we will have the distribution for the sum x plus y. So this equality will give us the proof of the statement. So let's write this. So this probability is equal to the following. So I know that x is equal to k, and then here y is equal to n minus k. Yes, and now I use independency. So here independency probability is x is equal to k, probability y is equal to n minus k. And since x and y are independent by assumption. Now just write the probabilities, because I know the distribution for x gamma to the power k, k factorial, and here exponent minus tilde to the power n minus k factorial. So now my aim is to obtain somehow the Poisson process with parameter gamma plus delta. So I will create this distribution here, gamma plus delta over in power n divided by n factorial. So what I should add n factorial, k factorial, n minus k factorial. This is good. We have now binomial coefficient. This is good. And here I have gamma to the power k. And I should divide by this gamma plus delta in power n, but I will split it in two parts to the power k. And as you can understand, here I write gamma plus delta n minus k. That's right. So now we have here exactly Poisson distribution, and here we have binomial distribution. Yes, here we can see that here for p I take gamma plus delta, and 1 minus p, exactly this delta gamma plus delta. Yes, so for Poisson for binomial distribution, parameter p is equal to gamma over gamma plus delta. So this is exactly what we should get. I will just write once more. So we have Poisson distribution with parameter gamma plus delta multiplied by binomial distribution with parameter. We have n at total. P is equal to this gamma plus delta, and this is the probability that random variable is equal to k. So now what if I will sum this probability over k? Sum over k is probability that x is equal to k, x plus y is equal to n. On one hand side, I will have just probability that x plus y is equal to n. Yes. And here, since we have here the distribution, so we will have here the Poisson probability with parameter. So indeed, the sum of x plus y have Poisson distribution. And here, the second, so we just need to write conditional expectation by conditional probability by expectation. So you just should divide this by distribution of x plus the probability x plus 1 y is equal to n. So you will have the binomial distribution. So this is how you can understand this proposition. So as for me, this is rather interesting. Now, some sort of opposite to this, but not so opposite. So let us somehow start from one point process, but we will separate points from one type into two types. So if I have a Poisson distribution of random variables, so I have some points. So this will be random variable z. So with these points, you can understand, imagine that we have this random points from the third example that we obtain as limit of binomial. And now I will create two types of particles. One of them I will remain alive, but one of them I just kill. Independent and randomly with probability P. So I take a particle, and with probability P, it will be alive, and with probability 1 minus P, it will be dead somehow. So now this is the way how we can create two types of particles from one system. And now let us find the connection between where here we can find binomial and Poisson distributions. So let us write a proposition more precisely. So let us fix Poisson random variable z, Poisson random variable with parameter gamma, and fix P from 0, 1. This will be the probability how we can separate the points here. And let us now define the procedure of separating. So let us define random variables zi, PIID random variable. Each of them has Bernoulli distribution. Or binomial with parameter 1 and P. So I will write that I is equal to 1 with probability P and 0 with 1 minus P. Okay. And now I form a random variable X. I will sum from 1 to Z. Oh, here the important part that Z also independent on this random variables Zi. This notion I will use for independency. Okay, and here I take the random number of summation of this binomial or Bernoulli random variables Zi. So you can imagine that for X, we put the points here, which is equal to 1. Yes, and the rest of them, X, then X will have again a Poisson distribution with parameter P multiplied by gamma, difference Z minus X. So this means that this is the rest of particles. So this what alive, and Z minus X what we kill. It is also have a Poisson distribution. And moreover, these random variables are independent, and X independent of Z. So this is the conclusion of this separating of points in such picture. So we separate them using this procedure. So we just take one of them equal to 1 and 0. You can imagine here 1, 1, 1, and here I put 0. And so this random variables will be Poisson and independent. So let us prove this. Let us prove. So first of all, note that if I know the number of points, if I know the value of Poisson random variable here, then X will have a binomial distribution. Yes, because as we, from the beginning of the lecture, we saw that the summation of Bernoulli random variable with fixed number of summation is a binomial distribution. So here the same is true for conditions. So if I know that we have exactly m plus n summation, for example, yes, then this probability is binomial of what? Of a total m plus n summands with parameter p, and p calculates the probability is equal to m. Okay, so this is when we know the number of summation. So to prove the statement, again, I will prove statement. What we should prove? Again, I will consider the probability of these two events. M is X is equal to M, and difference is equal to N, for example. And if I prove that this is the product of Poisson P gamma M multiplied by Poisson 1 minus P gamma M, then this is all, yes, because we have the product of probabilities and we have exact values. So let's do this. So left-hand side, probability X is equal to M, Z minus X is equal to N. This means X is equal to M and Z is equal to N plus N. So now I will use this conditional probability. So I should write the probability that that is equal to N plus M multiplied by conditional probability equal to M with condition. So now we know these probabilities, and all we should do just put them together. So this is by definition, by assumption. This is the Poisson distribution with parameter gamma. So I write its probability. And as we say, this conditional probability is binomial. So I write binomial coefficient. And here parameter p, yes, because each summand is the Bernoulli with probability p. M 1 minus 2 to the power n, because this is m n plus n minus n. So from this, I should create two Poisson probabilities. So I will split this exponent into two parts, p gamma and exponent minus 1 minus p gamma. So this is from this part. Now I have this p to the power m and gamma to the power m. I have gamma p to the power m and the same gamma 1 minus p to the power n. And now I have here, I should divide by m factorial. And here I should divide by n factorial. Maybe let us, I will not do this. I will just write this binomial coefficient. This is m plus n factorial divided by m factorial, n factorial. And we can see that this, we have here n plus m factorial from this part. So they did disappear, and we have 1 over m factorial for the first part and n factorial here. So as we wanted, we have a Poisson distribution with parameter n gamma probabilities equal to m, and Poisson, the Poisson probability with parameter gamma 1 minus p, that random variable is equal to n. So we have the product. So these random variables are independent and have desired distribution. So this is the end of the proof. So we considered two properties of distributions, and the most important part that we consider them not only as a property of random variables, but we consider them as distribution of points. So this is most interesting for me. And later we will consider in more details. So today I did not give you precise definition of a point process. We will do it on next lecture. We will consider point processes random measure, and we should define it more precisely, because it's not so easy for arbitrary case. And we will see that Poisson distribution plays a big role in point processes. And for homework, maybe as exercise, I would like to give you exercise. I would like to give you another characterization of a Poisson distribution. But to do this, I should give you some notation. Denoted, not very. So by this notation, I will denote the such factorial product. So n multiplied by n minus 1 and so on, multiplied by n minus k plus 1. It's so-called descending factorial. So with this notation, please try to prove the following. So if I have x, a Poisson random variable with parameter gamma, then the expectation of this descending factorial, so x k, is equal to gamma to the power k for all k from natural number and 0. And why do I say that I give you another characterization of a Poisson random variable? Because this is true only for Poisson random variable. So if I know that x is an zero-valued random variable, and there exists a constant gamma such that we have this property xk, k. Then from this follows k for all k. From this follows that x has Poisson distribution with this parameter gamma. So this is another characterization of a Poisson distribution using its moments. Yes, you know that if you know moments, all moments of random variable, you can say the distribution in some cases. But here we use not just moments, but so-called descending factorial moments. So this is for your homework, and if you will try to prove it, we can discuss it next time. So this is all for today's lecture, and if you have some question, please ask.